Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2024 Northern Hemisphere Methods Exam 1. So just before I start this video, I just want to say thanks to Mark who sent this, who sent me this paper early. I will link his channel in the description. Please go check him out. He's a great guy with great methods videos. Also, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. Just a disclaimer, these are my suggested solutions, as basically VCA hasn't posted the solutions yet of this exam. I just wanted to make these solutions so students can mark their answers to these solutions and basically help them understand how to do the questions. If you have any questions or might see me make a silly mistake, please let me know. Remember, I am a human. I will make sometimes silly mistakes. I hope these solutions help with your method studies. Also, I am going to be very, very detailed in my answers because I want to help as many students to understand the concept. So, yeah. So basically, I'll go over time. I'll go, now normally you're given like 1 hour to this exam. I'll try to go as detailed as I can. And yeah, I'll probably go over time more than the exam period time. Yeah, I hope this video helps you and let's do this. Question 1. Let's have a look at this question. Let y equals x squared plus 1. Find the factorized dy dx. You should straight away realize that this is the product rule, where this is your u and this is your v. So our u in this case is x, and our v is ex squared plus 1. Beautiful. Find u dash, so find the derivative of u, which is 1. Find v dash, which is the derivative of ex squared plus 2. One of the quickest way is just to derive the top part, which is basically 2x, multiply it by the same function, ex squared plus 1. Beautiful. Now, the product rule formula is dy dx is u times, so basically u times v dash plus v times u dash. So basically like this, you multiply this first plus multiply these two. So, let's do it. So your dy dx is going to be 2x squared ex squared plus 1 plus ex squared plus 1. Beautiful. Now, remember, we found it. So that will basically give you like a 1 mark. But you remember, you need to factorize it. So what is the common factor here? It is x squared plus 1. So let me just write dy dx here. Dy dx is equal to ex squared plus 1, 2x squared plus 1. I hope that's correct. Have I made any silly mistakes? Looks quite good. All right. I hope that's perfect. So here, this is the first answer. Let's move on to the next one. B, let f of x be this. Evaluate f dash of x at x equals e. Beautiful. So this is the quotient rule. So we let u be the top function and v be the bottom function. So let's do the same process. So u is x cubed, v is log e of x. So basically u dash is 3x squared, v dash is 1 over x. And remember the formula for the product rule, the quotient rule is f dash of x is v times u dash minus u times v dash, all divided by v squared. One of the quickest way that I remember this is, remember how the product rule, we started by multiplying this plus that? Do the opposite way. So multiply basically like these first, then not putting plus but putting a minus, and multiply these together. And then at the end, just divide it by v squared. Beautiful. So now that should result me in what? So f dash of x, so basically 3x squared log e of x minus basically x squared, because when you multiply x cubed by 1 over x, you get x squared, all being divided by velocity, not velocity, v squared, which is log ex squared. Now, basically, this will give you 1 mark because you found the derivative. The second mark comes by subbing it in and getting the answer. So, f dash of e is 3e squared. Now, if you sub in e to log e of e, because they have, the base is e, and you're subbing e on the x, it becomes 1. So that's, yep, minus e squared, all being divided by, again, just remember you sub an e here, it's going to be 1, and you imagine squaring 1 is just 1. So that is it. And you're basically left out with the answer, f dash of e is 2e squared. Beautiful. Nice, easy. So every exam, you will always start with derivatives. So nice to, 4 marks. Let's move on to question 2. So question 2 says, consider the simultaneous linear equations. So we have these two equations, where a is an element of all reals and x and y are elements of all reals. Find the value, not values, so there has to be one answer, for a, for which there are infinitely many solutions. Infinitely many solutions. Okay, say, let's consider this as line 1, and let's consider this as line 2. So actually, let me do it in different colors, so to kind of visualize it much easier. Let's consider this as L1 with yellow, and this is L2 with this green color. If we want to, so if I draw the straight line of line 1, and I draw also like a let's say they have the same gradient right now. This is your line 2. If we want them to have infinite many solutions, they must be on top of each other. So this on top of that L1, meaning that basically they intersect forever, meaning that we get infinitely solutions. That's what it is. And what are the conditions that must be met for that to happen? Easy. Well, having a look at this, we know that the gradients must be equal. So M1 means the gradient of line 1 must be equal to M2. So the gradients must be equal of these two equations. Also, the y value has to be the same. Both y values, so y1 must equal to y2. Beautiful. So if I was drawing this like nicely in a Cartesian plane, it would look like this. It would be like a function like this. Like that. Two functions on top of each other. And you can see that the y values are always going to be at the same part here, and the gradients are the same. So this is the condition for infinite many solutions. All right. Now I'm going to show you 2 ways to do this question. You can do the normal way. I'm going to show you the normal way first, like the actual conceptual way, and I'm going to do the quick way. Now normally in an exam, do the quick way. It's much more better for you. But I'm going to show you the conceptual way. Okay. So now these equations, these straight lines, they're not written nicely. Like we want to write them in like y equals mx plus c form, because why? Well, we can easily find the gradient and we can easily find the y-intercept. That is why we want to write it in this form. So we're just going to basically rearrange them. So let's rearrange L1. So L1, so let me write that nicely. L1 is 3 minus ax, all being divided by 2 minus a. That's it. So basically, this is the line. That's basically the line. Let me write y1 equals to show that. So y1 equals that. So what is our gradient? Well, our gradient is negative a divided by 2 minus a from the equation. And our y-intercept is 3 over 2 minus a. Beautiful. So we got the gradient and the y-intercept in terms of a. And we're going to do that with line 2. So line 2, same thing. y2 equals what? So this is 2a plus 1. I'm going to minus x, and then I'm going to divide them all by a. Now this here is my straight line equation. So my gradient, looking at this, is what? It's negative 1 over a for this equation. And my y-intercept, so y2 is, looking at this, it's actually 2a plus 1 divided by 2a. Because what's happening is this is dividing by a, and so it's going to reciprocate. Beautiful. All right. Now, how do we do this? Well, let's try to make them meet the first condition, which is the gradients must equate to each other, must be equal. So let's equate the gradients. So gradient of this equals that gradient. That's what we're going to do. So negative a divided by 2 minus a must be equal to negative 1 over a. Now, because there's two negatives on both sides, we can actually get rid of that, negative and negative. Now, I'm just going to do cross multiply. So cross multiply these two to get rid of those divisions. So it's going to basically be a squared equals 2 minus a. So a squared plus a minus 2 must be equal to 0. So factorize that. What do we get? A. So 2, 1, is it negative here? So it goes 2 minus 1. Yes, that works. So hence this factorizes to a plus 2 and a minus 1 equals 0. And so solving that, I get a equals negative 2 and a equals 1. Basically, these are the values of a for which the gradients are going to be the same. All right. Now, these are not your answers. Be careful. We need to check if the second condition is being met, which is that the y-intercepts for both have to be equal. Now, that's a kind of an easy test because, now, I'm going to make this small. I'm going to kind of make this small because we've kind of took a lot of space. Now, it's going to be like a guess and check. So, what I'm going to do is, I'm going to try to put this here, right over here. Okay, these are our two. This is what we're going to do. We're going to check. So I'm going to check first. What am I, Robert? Check. I'm going to check first the first one. A equals negative 2. So let's sub a equals negative 2 to the y values. These, if I sub an a equals negative 2 on them, they should have the same. If they have the same y value, then they are infinitely many solutions. That's great. So let's do that. So subbing it in y1. So y1 will give me 3 over basically 4. And y2 equals what? Negative 4, so negative 3, negative 4, which is 3 on 4. Beautiful. You can see that when a is equal to negative 2, the y values are the same, basically meaning that condition has been met. So actually, a equals negative 2 is a solution. Now, we need to double check a equals 1. So, we just have to do a guess and check again. So I'm just kind of concerned about the space that I've done here. All right, I'm going to write it a little bit at the bottom. So we want to say that y1 equals y2 for a equals negative 2. Beautiful. Now let's check the other case. Check a equals 1. So let's sub that into those y. So y1 is going to be what? So if I sub in 1, it's basically 3. And y2 is going to be 3 over 2. Nope, they are not the same. y1 is not equal to y2. Hence, a equals 1 is rejected. Reject that. So, and that is it. So, let's write a nice general answer because this looks like a mess right now. But so, basically, this is your answer right over here. Reject a equals with 1 because it doesn't meet that condition, that last condition. I hope that kind of makes sense. So I want to kind of make it smaller and write my answer. So take all this, put it right over here. I'm just going to kind of... Okay, so I'm going to say reject a equals 1. Hence, a equals negative 2. That is your answer. Basically, this should only be your answer. And we are meeting the condition because it's saying find the value, only one value. Beautiful. So that is the first way to do it. Now, look, it does take a lot of time. You can see how much space it takes, but there's always a quicker method, and that's what I'm going to do next. So the quicker method is actually called using the determinant. Now, let's do that. I'm going to use a actual different color to kind of... So let's use nicer color to kind of show the determinant. Let's use... Ooh. Oh, not a very... Not cool. Okay, let's use this color. Let's see right over here, but let's use this green. All right, let's do it. So to use the determinant, what do we do? Well, it's quite easy. You need to have both, graphs, both lines to be in this form, like ax plus like by must equal to some constant. So for example, this one's perfect because you can see ax, y, 3 and that constant. Same with the other one here. Normally, they're going to be giving it like this. I'll be honest with you. Normally, when you do this question, they always give it in this form. So that's why it's such a quick method. And so now, this is what the determinant does. What you're going to do is draw a matrix. And what you're going to do is the first value, like for example, the x, we're only dealing with the constants in front of them. So for example, the first one is a, so put a here. The next to it, the y, is 2 minus a, so write 2 minus a. You don't worry about those constants. Just keep whatever is next to the a's and stuff, that's what we worry about. Well, let me just move this. Like that. All right. We do the same for this one. We can see that there's, constant 1 here, and this one, a. And remember, this is just basically a constant. We don't worry about it. That is it. Now, this is what the trick. What you're going to be doing is doing this. To find the determinant, you're going to multiply these first here. A times A. It's always going to start from the top left to the bottom right. Always. So, A times A, which is A squared. And you're always going to put a minus. And then do the same for these two here. 1 times that is basically 2 minus A. And you let that equal to 0. And so, doesn't that look similar? So similar to our, say, plus a minus 2 equals 0. Look how quickly we went to the quadratic equation compared to all this work just to get this equation here. So you can see how quickly this is. And basically, when you get this here, your life is so much easier. Then you just basically check if these values are going to meet that condition, like what we did. So I hope that is another method. So great method to speed it up. Let's do the next question. B. Find the values, look at the word values, of A for which there is a unique solution. Unique solution means they basically cross once. Now let's look at the conditions for them to have a unique solution. So this is line 1. And this is line 2. For them to always basically cross each other for a unique solution, their gradients must never be equal to each other. Never. That's the condition. For example, we can see that the gradients are never equal to each other because if the gradients are equal, what happens? So for example, let's say gradients are equal. This is your line 1 and this is your line 2. They will never cross in the long term. Never ever. They're just going to go parallel to each other, basically. And if they, even if they even had the same gradient, they could have that condition where basically, okay, they have the same gradient, but then there's a condition that they will have infinitely many solutions. So overall, it doesn't matter. You just need to make sure that the gradients are never equal to each other. Beautiful. And well, now what about the y values? That's the question. Now, the y values doesn't matter because if the gradients are, not equal, they're always going to cross once. For example, let's look at a condition here. So we draw a graph here. So we have a graph, so we have another graph here. You can see that the gradients are basically not equal, which is the unique solution condition. And you can see that they have the same y value, but they still cross out that value once. So this is what we call unique solution. It doesn't matter. Or what about if so you can see that if the y values are equal, what about if they're not equal? Still meets the condition. Like for example, if you have, in this case, we have something like this. And another one goes like that. You see, they cross once, but they have totally different y values. So absolutely, the y value doesn't matter. It's all about their gradients. We need to make sure that their gradients are not equal to each other. Now, that's quite easy. Because didn't we know that when the gradients are equal, this condition, when the gradients are equal, so the values of A for which the gradients are equal are A equals, we just calculated, which was -2, and A equals 1. Wasn't that true? So if our A values are -2 and 1, the gradient's equals, and then there's no unique solution. So basically for unique solutions, it's all values, infinite values, except these two values here. Because if these values are put in there, they're going to make sure that we're going to have the same gradient, which is a big problem. So basically, yeah, our answer is all reals, so all values except these two. So let's write that down. A is an element of all reals, so all numbers, except -2 and 1. Beautiful. Nice. So that is that one here. Next question. Find the value, so there has to be only one, of A such that the lines meet at right angle to each other. Right angle to each other. Well, doesn't that already remind me of something? So if I kind of graph L1 here, Say this is L1. And say this is L2. So your second equation. If they're going to be basically meeting at right angle to each other, you should remember the perpendicular gradient. So, for example, you remember this ratio, this value. So if this was M1, sorry, let me write it. So if this has a gradient of M1, and this one over here has a gradient of M2, so because, think of it, so if we can see that because they are perpendicular, it means the gradient of M1, let's say if we were trying to find M2 basically, it's going to be equal to -1 over M1 if they are perpendicular. This here, I don't even know what you call it. It's like perpendicular formula to find the gradient. To find the perpendicular gradient, it's this formula. To find the perpendicular gradient, this is our formula. Where, because if they are perpendicular to each other, if they meet at right angle, it means that the gradients have to meet this condition. Where M2 is equal to, or it could be vice versa. M1 equals -1 over M2. So, yeah. They have to meet this condition. So that's our answer, basically. So let's make sure we equate it like this. I'm going to put this down. Make it a little smaller. And let's do it. So, M2. Where was M2? Didn't we hear? So M2 is right over here. It's -1 over A. -1 over A must be equal to -1 over M1. So what is M1 again? M1 is -A, 2 minus A. So -A, and it is, so -A, 2 minus A. Beautiful. Now, both have negatives, so you can cancel those negatives out. And you can actually, reciprocate it. Reciprocate both. Because you know how it's one, they're both divided by, like, 1 divided, 1 divided. Yeah, just reciprocate. This equals the bottom part. So A equals -A over 2 minus A. Have I made any algebraic mistakes? Does not look like it. Perfect. So multiply both sides by 2 minus A. So 2 minus A equals -A. Expand this out. So A squared minus A minus 2A equals 0. A squared minus 3A equals 0. So A is A minus 3 equals 0. Hence A equals 0 and A equals 3. So we get actually 2 values. Now, of course, it has to be 1 because the answer tells us find the value. So we need to check if they both, meet that condition. Like if I kind of, have a look at, we have to have a look at them. I'm just going to rub this out. Okay, so we got these 2 parts here. We need to double check them. So what I'm going to do is I'm going to copy this original equation. The things that gave us the equation of the line. I'm going to basically copy, paste it here. All right. So I'm going to check A equals 0. So if I sub in A equals 0 into, y1, it'll become what? So it'll be 3 over 2. So it'll just become y1 equals 3 over 2. That's our equation. It's just a horizontal straight at 3 on 2. What about y2? If I sub in 0, rubbish, does not work. Why? If you sub in 0, the denominator becomes 0. And remember what happens? If your denominator becomes 0, it's undefined. So that's absolutely rubbish. It doesn't work. A equals 0 doesn't work for this equation. Hence, that's why it's not considered. So yeah, our answer has to be A equals 3. Because when you sub in A equals 0 to this, remember, it's at the denominator. It's undefined. So absolutely. So reject A equals 0 and, it's A equals 3. Now, we can also just check A equals 3. I mean, we have the time, so let's do it. So imagine subbing to y1, so 3. Be 3 minus 3x, all dividing by 2 minus, so -1, which is basically, you can write it like that. That's our y1. What about our y2? So if I sub it in 3, so 3 times 2, which is 6, plus 7, so 7 on 2, minus x, all being divided by 3, which is basically 7 over 6, minus x on 3. Aha, you can see that the gradients are perpendicular to each other. They meet that, equation, so m1 equals -1 over m2. See that the gradients are, meeting that condition. And yeah, their y values are different. So if I kind of graph them, let's graph them to see it. So let's draw this one. So it has a positive gradient and -3 is its y-intercept. So it'll look like this. Then this one here has a positive y value and it's negative gradient like this. And we can see that they will be perpendicular. Beautiful. So our only answer has to be a equals 3. So all this working out just for 1 mark. But yeah, it's quite easy. You straight away. I hope that makes sense. Yeah, a equals 3. So make sure a equals this reject. Reject. Beautiful. For 1 mark, you just write a equals 3. But yeah. Question 3. Let's have a try at this one. Okay. Function d, f of x is given here, where d is the domain for f. State the maximal domain for f. Easy. So we know that to find the maximal domain for any logs, it's so easy. Make the inside function here have to be greater than 0 and solve it. Remember, because inside of a log, it always has to be greater than 0. Not equal to 0, but always greater. So what we can do is just this equation here, for it to be defined, it has to be greater than 0. And we basically solve this and we get our domain. So -2 on both sides. We get this. Divide both sides by -1. But be careful. Because it is an inequality, if you divide by a negative number, the inequality, sign changes to 2. Hence, this is your domain. So your domain, your dom of f is basically negative infinity to 2 non-included. So 2 is not included. Beautiful. So let's highlight that. Nice. Next question. Sketch the graph of f of x, labeling the asymptotes with its equation and the axial intercepts with their coordinates. Easy. So one of the quickest ways to find out the asymptote, that vertical asymptote of a log, it's just to solve the inside and let it equal to 0. 2 minus x equals 0. So it's basically at 2 if you solve that. So if I just draw kind of a horizontal line, and then I kind of rub it to make it like a nice, asymptote equation. So if I just rub that out now and just duplicate this as many times, make a nice like that. So sorry about this. There it is. All right, there it is. Okay, and so that's our equation. X equals 2. Okay, how is this log going to look? Let's think about it. We know a log, like a normal log, looks like this. We know a normal log would look like this. So it would look like, so in this case, it's just basically like this. This was a normal log. Okay, this is the log e of x. That's how the graph, and we have an asymptote at x equals 0. Now, what's happened here is it's basically translated 2 units to the right. So imagine you translated 2 units, and that's where our asymptote is. But there's also a reflection. There's also a reflection along the, along the y-axis. So think of it like this. So you first reflect it. It's going to look like this. And then you translate it 2 units to the right. It will look like that. So that's your function. Beautiful. So it will look like this, basically. Oops, why is that? All right, beautiful. It looks something like this. Yep, like a nice log. Looks like that kind of shape, and it goes towards 2. Now we just need, so we've found the equation and we've labeled it. Now we need to find the axial intercepts. Easy. So let's find the y-intercept. So to find the y-intercept, we just let x equal 0. If I let x equal 0 here, it's just basically 3 log 2. So this here. So if I let the, basically, x equals 0, it becomes 3 log 2. Just want to make sure. Don't want to move it there. Okay. Is that right? So 3 log e2. Beautiful. So that's the y-intercept. What about the x-intercept? Let's solve it. We let y equal 0. So 0 equals 3 log e2 minus x. So you divide both sides by 3, which is 0. Log e2 minus x. E to the power of 0 is equal to 2 minus x. 1 equals 2 minus x. and it's x equals 1. So our x value, our x-intercept's at 1. Now, look, this is not close to 1, so it's actually midway. So let me just kind of move this, translate this a little bit more to the right to, make sure it looks like the same. Like that, there it is. Make sure, like, this is your y-intercept here. There it is, so that's your y-intercept. Now this here is basically 1, 0. Nice. Nothing wrong with that. Beautiful. Everything's excellent set to the coordinates and done. Next question. Find the values of x for which f of x is basically between 0 and 3. Easy. Let's do this. So think of it like this. I'm just going to take a screenshot of this. Okay, I'm just going to take a screenshot of it to kind of show you. So we can just... All right. I'm going to... Okay. Just paste the same diagram here, but now I'm going to label the diagram. Okay. Okay, so here it is. So this is your... Ooh. Let me make it smaller. Okay. So this is the actual function f of x, yeah? So imagine I'm going to do some colors. So imagine f of x is this. We know f of x is the yellow color. It's this yellow graph that basically is here. It's that yellow. And imagine just to be so basically equations. Y equals 0 and y equals 3. So just straight lines. So y equals 0 is this straight line that goes like that. And y equals 3. Now, where does y equals 3 lie at? Between, it would be less than this. Why? Well, think about it. Log of 2 is like greater than 1. If I'm not, is it? So if I, yeah, it should be greater than 1. Then tripling it, it's going to be greater than 3. So this here is very large. So 3 should be around here. So it has to be smaller than the y-intercept. Okay, so y equals 3. Okay. So basically what this is telling you is when is the yellow graph, this f of x, between these two functions, 0 to 3? Well, it's quite visibly here. It's from here all towards here. This is where it's between them. And so basically we just need to find the x values. Now, of course, the x values are from here to the x-intercept. So let's find this value over here, this value here. Now, that's quite easy. Isn't it basically when... the y equals 3 line, equals the f of x function. So yeah, and we can find that x value here. That's what we're going to do basically. So let's do that. So f of x was what? Originally, what was the function? 3 log e 2x. So 3 log e 2 minus x, was it? 3 log e 2 minus x. Yep, and we're going to equal that to 3 to find that x value here. Okay, divide both sides by 3, we get log e 2 minus x equals 1. E is 2 minus x, and hence x is basically 2 minus e. Beautiful. So this value over here is 2 minus e. And so we know already this is 1 because it's basically the x-intercept, so 1. So your domain is what? Because they're also included, by the way. They're also included from these arrows. So basically your the values where basically f of x is between 0 and 3 are from. So x is an element. So I'm going to write it in terms of like the x is the element. The x value that f of x is between 0 and 3 is from 2 minus e to 1. Or both are included. That is your answer. Beautiful. Not too bad. So 2 minus e, yep, to 1, and they're both included. All right, perfect. So let's do question 4. Question 4, let G be this with that. So that's actually in its maximal domain, okay? And h of x is that, okay, also in its maximal domain. Show that G of h is defined for all x as an element of all reals. Now, look, there's 2 ways to do it. I think this part here. Now, we're going to do like the methods way, like the actual methods way they probably teach you at school. So let's do that first. So G of h of x, basically written, oh, oops, not wrong thing. So that's the same as G of h of x. Now, for this to be defined, for this composite function to be defined, it needs to meet this condition. So G of x to exist. So basically, for it to exist, it must meet that the range of the inside function, which in this case is h, must be a subset of the domain of the outer function, which in this case is domain, which is g. And so what is the range of h in this case? Well, basically the range is, if you kind of graph this quickly, you graph this, you can see it's, you have an asymptote y equals 2, just a normal asymptote. So basically 2 to infinity. So there's a color here. 2 to infinity is the range of h. It has to be a subset to the domain of g. What's the domain of g? It is this over here. So let's write that down. 3 on 2 to infinity. Beautiful. So, like, is it a subset? Is 2 to the infinity to a subset of 3, like 3 over 2 to infinity? Well, just kind of put them in the number line and see if it makes sense. Like, for example, I'm going to make this color here. I'm going to make this one over here basically like blue, and this one here red. And I'm going to draw a number line. Let me draw a nice number line here. So 2 is here. Let's say 2 is here. So 2 to infinity. So that here is just an open circle and goes towards forever to the right. The next one, which is 3 to, it's red. So this one's red. It's 3 on 2, which is around here, to infinity. Something like that. There it is. Beautiful. This is what we're saying. This is what we mean. We're saying, does 2 to infinity, so does the blue graph fit? Does it like fit in the red graph? Yes, it does. You can see that actually does. So it does exist. So basically it does. So we can say hence the range. Basically just rewrite the thing. The range exists. The range. I'm just gonna basically copy this. Duplicate. Exists, which means basically g of h of x exists. Beautiful. I think that will, now this will give you 1 mark to prove that that the function exists. But of course, what we're trying to prove is is it defined from x as an element of, or really meaning that is the domain of g of h of x that? Well, easy, because now we know it exists. We know that the domain of a composite function, if it exists, is equal to the domain of the inner function, so h of x. Now, we already know that the domain of h of x is what? All reals. So this lets me know that, so hence, g of h is defined for all x is an element of all reals. Beautiful. So that is like the original normal way, you know, showing that's a subset. But I also think that there's like, if I was in the exam, to be honest, like in terms of just, I think there could also be this possibility that you can do it this way. So I'm just going to put this at the bottom. I'm going to show you the other way that you can also probably do it. It's just by algebra, explaining it by terms of algebra. Let's explain. So we know that g of x is what? So we know that g of, this is what we're trying to prove. G of h of x. So let's actually write the function, which is basically means g, so log e 2e 3x plus 4 minus 3. So g of h of x, so you're basically subbing h of x, so sub that into that, all of the x values, and you should basically get log e 2e 3x plus 1. All right. Now, remember what we said from the original equation. Remember from this. To find the domain... Oh, not this one. Remember this here, log? Remember how we said the domain of a log is easy. You just basically solve where the inner function is greater than 0. And let's do the same here. So we can say for... Basically, so for log of 2e 3x plus 1 to exist. So for it to exist, the inner function, which is 2e 3x plus 1, must be greater than 0. It must be greater than 0. And let's see if it is. So I'm going to bring that minus 1 to the other side. Is greater than -1. And let's be honest. You should already know, since we already know that, remember exponentials are always greater than 0. Since we know, 2e 3x is always greater than 0. Remember, exponentials are always greater than 0. For all x, so for all x is an element of all reals. So for all x values, we know that always an exponential is greater than 0. This inequality holds true because remember, so if we know that 2ex is always greater than 0, so like, 1, 2, so let's say it's 1. So sub in 1, is 1 greater than -1? Yes. Is 2, imagine subbing 2. 2 is greater than -1. Every value, because we know 2e 3x is always greater than 0, this inequality is always true. Hence, g of x is defined for all x, it's an element of all reals. So basically, this proves to us also that because this inequality is always true, you say, is always true. Hence, g of h is defined for all x is an element of all reals. Beautiful. So these are two ways, I think. Now, of course, do the first way. First way is kind of every teacher knows how to do the first way. The second way is a little bit more algebraic. You should know that too. Yeah. So, but both ways, I think, would still give you the mark. But I think do the first one. The first one is basically the normal way to do it. I hope that kind of makes sense. And yeah. So I don't know where to put this. I'm going to basically put this at the bottom. So I'm going to try to do the next question. Overall, this paper is quite nice. I haven't seen any... It's not as hard as it, right? I haven't seen a hard question, which is good. So let's do this one here. Find the range of g of h, given that the domain of g of h is all x as an element of all reals. Now, we know that g of h had that domain. So we just need to find the range. Okay, let's think about it. So let's write g h of x, which I think we wrote it here, which was log e 2e 3x plus 1. Okay, how would this, like, if we were to graph it, we know that, domain's all reals, but if we were to graph it, how would it look? Well, let's think of it like that. So first sketch that 2e 3x plus 1. That's how I would do this. First sketch it. All right, let's first sketch it. So we got, it has a, asymptote at y equals 1. It's this nice, beautiful thing. Now remember, these are your y values. So like, if, for example, you know how we know x is an element of all reals? So if you sub in 1, like, x equals 1, this is going to be always greater than 0. It's always positive. Sub in 2, 3, but it always grows larger. So the more x values, the higher the x values, it grows larger. So it's fitting this, basically, this graph, basically. And if you're just going to log it, it's just basically going to, so think about it like this. Okay, we know that, say this value here, it's positive. We know it's positive. And imagine you just log a positive number. It's just log. It's just a log. So it's the same thing. What about this number? Now, we know that this number has a higher value. Now, you're just going to log it. It would have a higher value than the initial. So it'll still look the same. And you do that for top, doing the same. It will just basically look like, now this is an estimate, but basically it'll look like this. Like that, infinity. When you go to infinity, it'll look like this. It's just going to grow exponentially, the same as a log. So that doesn't change. But what happens as we go down to the left? Now we can see that our values are approaching a value of 1. Remember, because of that y equals 1, that asymptote. Now, if your values are getting closer to 1, meaning that this here is getting closer to 1, what does that mean? Imagine that log e of 1. If this is getting close to 1, we know log e of 1 is 0. So it would approach, and actually your blue graph would approach then 0. It has an asymptote at y equals 0, basically. It would look like this. Like that. Beautiful. So the blue graph is basically your actual log, an estimate of how the log is going to look like. So you can see that it has all this kind of the same similarity of this one over here, but the difference is as it's approaching negative infinity, because it was approaching 1, we know that would result in the log becoming 0. So it would look like that. So what is the range? We wanted to find the range. Well, we know straight away that the range of g of h is what? Well, we can see that because there's an asymptote here, it's from 0, non-included because of the asymptote, to infinity, because it can go to infinity. That is it. I hope that makes sense. little bit harder to explain. With no, like, yeah. Beautiful. I hope that's correct. Next one, let's have a look at question 5. So question 5 states that in a nursery, 90% of the seeds will grow into seedlings. Let p hat be the random variable that's representing the sample proportion of seeds that will grow into the seedlings for samples of size of 100. Okay, so let's do this. Find the mean and the standard deviation of p hat. Easy. So we know the probability of success. Oh, the wrong thing. Let me write it here. So we know that the probability of success is what? 0.9. It's to basically for the seeds to grow to seedlings. We know that the expected value for p hat from your formula sheet is just equal to your probability of success, which in this case is just 0.9. So what does that tell us? Just draw a new color. That the expected value of p hat is equal to 0.9. That is that one. Beautiful. Now we need to find the standard deviation. Easy. So for finding the standard deviation for p hat, it's in your formula sheet. It's basically the square root of p, 1 minus p, all over n. Which in this case is what? So let's think about it. So p is the probability of success, which I'm going to write it in fractions. So basically it's 9 on 10. Probability of 1 minus p is respectively 1 on 10. All being divided by n, which is 100. Multiply these two together, you get 9 over 100 here. And basically, like taking the square root of that, it's going to give me like the top square root is going to give me, so this one's going to simplify as 3 on 10. And the bottom part is just going to basically be 10. So what's 3 on 10 divided by thing? So it's 3 on 100. 3 on 100. That is your standard deviation. So standard deviation of p hat. Overall, not too bad, not too shabby. No, hasn't been, it's not, we haven't reached the hard question. So let's now do the next one. So let's say it be the standard normal random variable such that z, okay, we know the mean is 0 and the standard deviation is 1. And the probability that z is greater than -1 is approximately 0.84. So let's have a sketch of that. How would that really look? So if I draw like a nice normal distribution, let's say this here is your z. And let's just draw this. Nice. I mean, it's not the most... Okay. Like that. Okay. We know this is your mean. So we know the mean for z is 0. And the standard deviation is 1. And that's -1. And yeah. So basically, when we know that when z is greater than -1, so basically, draw a red line here. So basically this area here, which is your probability, is basically 0.84 approximately. That's what the probability of that is. Now, what are we trying to calculate? So using a normal approximation of p hat, estimate the probability that in a sample of 100, more than 93 seeds will grow into seedlings. Give your answer correct to 2 decimal places. All right. So we want to find the probability that more, so x is greater than 93 seedlings. All right. So look, straight away, one thing. We've done so much work because we're going to try to use the normal distribution for p hat. We want to make sure this is in p hat, not x. So remember the formula x is equal to, sorry, what am I doing? P hat is x over n. In this case, x is 93. So 93 divided by 100, which is your n. It's actually the same. You can rewrite this as probability that now p hat is greater than 0.93. This is what we're basically trying to calculate. So let's actually draw the normal distribution of p hat. So I'm going to kick that off. Now, I'm going to just copy this whole thing here. Take this whole thing. Okay, something like that. Okay, take this whole thing here. Oh, no. Should duplicate it, sorry. Duplicate right over here. Now this is going to be my p hat. I'm going to rub these stuff off here. This is your, basically p. And so we know the mean. What was the mean? We already calculated them. So the mean is 0.9 for p-hat. So this is 0.9. We know that the standard deviation, one standard deviation is 3 over 100, which is basically 0.93. This is going to be 0.8 7. Is that? Yep, that looks good. So what we're trying to calculate is the probability that it's greater than 0.93, which is this probability. All right. Now, you should know. Because of symmetry, isn't this probability here actually this probability over here? Yes, it is, because of symmetry. So, what do we know? We know that basically, all we need to calculate is that probability right over here. So, it's basically, isn't it just basically 1 minus? So, 1 minus the probability of this here would result us in getting the extra here. So 0.84. So 1 minus this here, which is that, will leave us with the green one here, which is basically 0.16 to 2 decimal places. Is that right? That looks good. So I'll just highlight that. Okay, perfect. Question 6. Let's have a try at this. Okay, let's do this. Question 6. Part of the graph of g of x here is shown. Okay, they've drawn the graph. Using the trapezium rule approximation method and 3 trapeziums of equal widths, estimate the area bounded by the graph of g of x and the x-axis and the line pi on 6 and 2 pi on 3. Easy. So we're saying from the line from here, so 2 pi on 6 to 2 pi on 3. So we basically want to estimate this area over here using trapeziums of 3 of equal widths. Quite easy. We know what the width is because look, one here, one here. We have now 3 trapeziums. They've kind of nicely done this question. So if I draw trapeziums, so that's one. That's one trapezium. The next one's here because the width of all of them is pi on 6 basically. That's another one. Doing another one here. Beautiful. So remember, there's actually a formula, quick way to do this very easily. So the trapezium rule, to do that, to find the area, this is the quick formula. It's just your width divided by 2 times. Where are you starting? Can you see how we're starting here? Pi on 6, and we're ending at 2 pi on 6. These are what we call special values. So for example, we start off pi on 6. These are going to be basically doubled. Let me explain. So we always start from the first, which is pi on 6, and then we're going to start, pi on 3, pi on 2, 2 pi. We're going to go one by one. So, but because your special, your starting value and your ending values are quite special. How? So you know your pi on 6 here, because it's a starting value. We write 2. Well, it's g, yeah. So 2g of pi on 6. What's the difference? You can see that basically they are doubled. The initial, so where you're starting and where you're ending are going to be doubled, whereas the other ones are just going to be normal. So plus the next one, which is pi on 3, because this is in the middle, it's going to be just basically g of pi on 3. The next case, pi on 2, so g of pi on 2. Now we've reached the ending. Remember your ending, your beginning and your ending are going to be doubled. 2g of 2 pi on 3. And that is it. This is your actual quick formula. And so now we just need to kind of simplify it. So let's do that. We know that the width is what? The width is pi on 6, we said. So pi on 6 divided by 2 is pi on 12. Okay, g pi on 6. Luckily, they've kind of nice. So g of pi on 6 is 1. So from that is 1. And you're going to double it. So 1 times 2 is just 2. Plus, what's g pi on 3? Pi on 3, the y value is 1.5, which is 3 on 2. Plus, g of pi on 2, which is 2.5, which is 5 on 2. Plus g on pi on 2, which is, so what am I doing? I'm just fully mixing myself up. Yep, so 5 on 2, and then g of 2 pi on 3, which is 3, but you double it, which is 6. And that is it. So adding these all up, so that'll be 8. So that'll be 8. Plus, so 3 on 2 plus 5 on 2, 5, 6, 7, 8. 8 divided by 2, which is 4. That's 12. So this is basically, that's going to be 12. These will cancel out, and you're left out with pi. So pi units squared. This is our estimation. Beautiful. So pi units squared is your answer. Next question, B. Let's have a try at that. So let h be from pi on 6 to 2 pi on 3 h of x, where k times g of x is h of x, where k is an element of all reals. So what's happened is, okay, so it's k is basically a dilation by a factor of k parallel to the y-axis. So all the y values are getting multiplied by k to make us h. All right, so g of x is the original. Yep. Using calculus, find k such that h is a probability density function. Easy. So we know that the area under a probability density function is always going to be equal to 1. So what do we do here? Well, think about it. What k values will be possible? Now, k actually has to always be positive, because think about it. If k, so basically, yeah, k always has to be greater than 0. Why'd they say all reals? I think they're trying to trick you. I think it could be a mistake, or think, why is that? It's because think about it. If k is 0, I mean, there's no function, doesn't exist. Or if k is a negative number, what's going to happen? This graph here is going to be reflected, like under. And so when you're finding the area under a graph, it's going to be a negative area. And remember, probability, cannot be negative. So a probability density function always has to be greater than 0. It always has to be above the x-axis. So the area is always positive. So yeah. So just be careful. So our answer when we do the question has to be like greater than 0. Your k value has to be greater than 0. So yeah, let's do it. So we know that the area under the graph. So let's write it nice. So we know that the area from pi on 6 to 2 pi on 3 of k times g of x. K is a constant. Take it out. G of x. Dx must be equal to 1. That is our expression. So what's g of x? I'm just going to write what g of x is. Sine 2x. Let's write that down. Sine 2x minus 5 pi on 6. Minus 5 pi on 6 plus 2. Plus 2 dx. Beautiful. Must all be to 1. So let's do it. So k is what? Let's integrate it. So it's a sine. So it's all going to say 1 over, derive the inside, which is just basically 2. And then the integral of sine is negative cosine. So negative cosine. Rewrite the whole thing. 5 pi on 6. Then 2 is going to be plus 2x. Close it. Pi on 6. 2 pi on 3 must be equal to 1. Have I made any algebra mistakes here? Looks good. So now let's sub in those values in. The first one is basically 2 pi on 3. So cos 4 pi on 3 basically. Minus 5 pi on 6. Plus 4 pi on 3. So when you're subbing 2 times 2 pi on 3, yep, 4 pi on 3. And so all this minus, now you're going to sub in pi on 6. So negative half cosine pi on 3 minus, is that, yeah, so pi on 6. Yep, pi on 3 minus 5 pi on 6 plus 2 times that, which is pi on 3. Yep, 2 times, beautiful. Close it. And that all equals to 1. Now we're just going to simplify this algebraic expression. So let's simplify this part here. What's 4 pi on 3 minus 5 pi on 6? Well, I hate this, but so it's going to be basically 8. You can read it as 8 pi, so equals 6. Yep, 8 pi minus 5 pi on 6, which is 3 pi on 6, which is pi on 2. So this here simplifies to pi on 2. And what happens, wait, we know that cosine, if you draw a cosine graph, that's pi in the middle. Pi on 2, the y value is 0, so this actually equals 0. So cos pi on 2 is 0, so this whole thing here is nothing but 0. Okay, that's simplifying good, that's good. So let's do the next cos one. So we need to simplify this here, this expression. Pi on 3 minus 5 pi on 6. So if I zoom into that'll be 2 pi minus 5 pi on 6. So right, 2 pi, yep, so minus 3 pi on 6. So basically it's negative pi on 2. Now because cosine, it has this special expression where you have if you have inside of a cos a negative angle, that that negative basically disappears. So it's basically the same as cos pi on 2, which is again 0. So great. This thing is actually quite simplifying nice. This here, it's all going to be 0 because it's going to be multiplied by 0. Now, all right, now let's simplify this. Oh my god, there's so much gaps, but it's basically 4 pi on 3 minus pi on 3 must be equal to 1. So let me just take this pi here. This is useless now. Okay, so this is going to be k equals pi, basically. Because 4 pi on 3 minus pi, yep, pi equals 1. Hence, your k value is 1 over pi. Beautiful, that looks good. I'm going to hope I haven't made any algebraic mistake, but that looks good. Next question, 7. Let x be a discrete random variable with a probability mass function of this. Okay, so this gives you the probabilities where x is an element of all. So z plus, your integers plus. Okay, be careful here. Z plus means 0 is not included. It's integers are like 1, 2, 3, 4, 5, blah, blah, blah. Blah, blah, blah. So 0 is not included. So, because it's saying Z plus, where basically, yep. So it's like 1, 2, 3, 4, 5. Those are the values only. And yeah, they're not negative and 0 is not included. So it's all these. And they're integers, meaning whole numbers. So what is find the probability that x equals 4? Easy. So, x equals 4. You sub it into this over here. Is so 2 over 3 on 4. So it's 3 to the power 4, which is what? So 81? Yep, 81 is it? 2 over 81. Beautiful. Not too bad. Next one. Find the probability that x is less than 4 given that x is greater or equal to 2. All right, easy. So just use the given formula. So, because we remember the given formula is first you need to find the intersection between these two. So let's do that. X is less than 4. Intersection x is greater or equal to 2. All divided by the probability of what is on the right using your given formula. Probability that x is greater or equal to 2. Now, let's simplify this expression using a number line. So if I use a nice number line here. So if I say this is 2 here and this is 4. 2 is in closed circle and goes to the right forever. And 4 is an open circle that goes to the left forever. When do they intersect? You can see that they basically intersect here. So that's what they're going to simplify to. It's going to simplify as the probability that x, so 2 less or equal, so it's equal to, because of that closed circle, x, where 4 is not included here. So that's not 4. All being divided by probability that x is greater or equal to 2. Done. Let's simplify this now. And like we said, remember that we're not 0. There's no 0. It's integers. So 1, 2, 3. So you're basically like x can only be between these. So if I kind of draw it like a nice probability density table like that. Oop, that's nice. So if I draw a nice probability density, so like your x, and to say this is your probability, your probability that x equals x or something like that. So we don't start with 0, it's going to start with 1, we said. Next one is 2, 3, blah, blah, blah. Goes forever, 4, 5, 6, 7, 8. And we don't know where it ends because it didn't give us a restriction. So basically, this is what it's going to look like. That's how our table is going to look. So if we're trying to find the probability for the first one, that it's between 2 to 4, but 4 is not included. So we're trying to find this basically. So 2, 3, 4 is not included. So basically just 2 and 3. So you can actually simplify this. It's probably that x equals 2 plus the probability that x equals 3. Done. Divided by, now what about the probability that x is greater or equal to 2? Ah, look at that. How do you do that? Given how we don't know when it ends. So we're trying to find the probability that it's 2 and forever greater than 2. Because we don't know where it ends. So what we can do is remember to do that. Isn't it, because you know how we know this probability of 1? Isn't it if we say 1 minus the probability of 1, don't we get left out with all of this? Like if we want to find the probability that 2 to 3 forever, can't we just say what's the probability of 1, but the one that's left out, and say 1 minus it? We will be left out with this here. So, 1 1 minus the probability of x equals 1. Beautiful. Now we're going to simplify this. Now that's not too bad because we do have the formula. So x equals 2. So the first one, x equals 2. So 2 over 3 squared plus 3, which is basically 2, 3 cubed, all being divided by 1 minus 1. So basically the 2, 3, which is basically 1 on 3. This is 1 on 3. It's just basically reciprocated. So it's the same as taking that 3, the whole thing here, multiplied by 3. There it is. So, I mean, take a 3 as a common, so if I take a 3 here and take a 3 from all of them, so like 1 on 3, so it'll be 2 on 3 here, plus 2, 3 squared. These cancel out. Take those out. And so basically this here is your answer. So we need to simplify it. So 3 squared is 9, so let's write 9 there. That's going to give me what? Okay, 9. So 9, 6, 7, 8. 8 on 9. 8 on 9. Yep. 8 over 9. That looks good. Hope my algebra is not wrong. Yep. So 9, 6, 7, 8. Yep, 8 on 9. Beautiful. Next question. Question 8. Let's have a try at this one. Let's use this color here. So we have f of x, and it's actually in its maximum domain. So 3x plus 1, that's in its maximum domain. Find an antiderivative for f of x. It says an. And means that you don't actually have to write plus c. You just let c equal 0. Normally, you can let it any value, but just let it just be 0. Don't put c. That's good. And so, yeah, we can write basically like f of x. Can we write it as 3x plus 1 to the power of negative a half? Because, remember, this is half, and then you put it on top, it'll be negative a half. So we can rewrite it like that. And so basically, if we want to find the antiderivative of this, of 3x plus 1 to negative half dx, it's going to be equal to what? Remember the rule. So it's 1 over. You derive the inside, which is 3. Add 1 to this, which is basically a half. Rewrite the whole function to the new power, which is a half. And that's it. So that's that here simplifies to 2 on 3 here. And so, that half, square root, that's going to become a square root. And you don't have to write plus c, by the way. That looks great. Have I made any algebraic mistake here? Does not look like it. Yep. The integral of that is 2 over 3 of 3x plus 1. Perfect. Okay. B. So for 3 marks, let's do this. The average value of the function f over from 0 to m is 1 on 3. Find the value of m. Easy, let's do it. So we basically, do you remember to find the average value? It's 1 over, you start off, 1 over, it's basically b minus 0, which is basically m minus 0, which is just m. Integral from 0 to m, your function f of x, dx. And that all should equal to 1 on 3. Now, we just learned that when we integrated f of x, didn't we just integrate it here, which is just this over here? So we can sub that in there. So 2 on 3. Oh, that's a constant. Take that, sorry, that's a constant. Take that 2 on 3 out. Make your life easier. So just leave it as 3x plus 1. And that 2 on 3, put it here. So this becomes 2, 3, like that. So if you take that, if you take that 2 on 3, it will become like that. 0m equals 1/3. Now, I mean, by basic, if because this has a third at the bottom, this has a, we can actually cancel those out. So basically, this is just equal to 1. Now let's sub in that m values and stuff. So it becomes square root of 3m plus 1 minus the square root of, if you sub in 0, it's just going to be 1. Equals 1. So, times both sides by 2 over m. I want to get rid of this. So it's going to be, no, m over 2. So multiply both sides by m over 2, you get basically 3m plus 1 minus 1 m over 2. Add 1 on both sides to get rid of that 1 here. We get this. All right. I'm going to make this as a common denominator. So that is basically m plus 2 on 2. So I'm going to square root both sides to get rid of that square root. So m plus 2. Square that. So yeah, like the whole thing squared basically. Let me just draw it. M plus 2 over 2, and you square it, which will become what? Will be m squared plus 4m plus 4 all over 4. Multiply both sides by 4 to get rid of that fraction. 3m plus 1 is equal to m squared plus 4m plus 4. So expand it out, 12m plus 4 is equal to m squared plus 4m plus 4. A half 4s, they're basically both sides by 4. Get rid of that 4. Minus 12m on both sides, so you'll basically be left with negative 8m. Yeah. That's going to be equal to 0. So now, solving that, so take a common factor of m minus 8 equals 0, so m equals 0, and m equals 8. What the hell? Of course, m equals 0 is not one of our answers. Of course, reject it. Makes sense, because we're going from 0 to m. Where basically m has to, of course, be greater than 0. If you're going from 0 to m, 0 is already included. Like, if you're going from 0 to m, of course, m has to be greater than 0. It has to be a number that's greater than 0. M must be greater than 0. Reject. This one here. Reject. So your only answer has to be this one over here. Reject. Beautiful. I hope that's no mistake on that. Now, I think question 9 is the last question. So let's smash this paper. Let f of f from 0 to infinity of f of x be this. Find f dash of x. Easy. So the product rule. So we're going to let u be this, v is that. So u equals x minus 1. V equals e negative x. U dash equals 1. V dash equals negative e negative x. Beautiful. So now, f dash of x, remember the rule. It's going to be these two multiplied, basically. So, negative e negative x, x minus 1, plus these two multiplied. So, e to the negative x. Now, I can see a common factor of e to the negative x on both sides. So I'm going to take that out. Which is negative x minus 1 plus 1. And so, simplifying this much further, we get negative x plus 1 plus 1, e negative x plus 2. Hence, this here is our answer. So let's write a nice statement. So f dash of x, e negative x plus 2. Done. Oh. Beautiful. Next question, B. So, state a sequence of transformations that map, so basically transform the graph of f of x to its f dash of x. All right. Let's have a look at that. So we're basically going, let's go up here and write. So there has to be 3 transformations because there's 2 dot points. Let's write it. So f of x is what? It's, let me write it nice. So I'm going to put that e negative x first. So we're going from this to this. E to the negative x. Negative x plus 2. Negative x plus 2. So, yeah, we need to say 3 transformations that basically transforms that to that. And what are they? Well, let's think. What are they? So, if we want to transform, what do we see? What's different? Well, the difference is the translations. That's the first thing that comes to me. This one's translated 1 unit to the right. This one's translated 2 units to the right. So if we want them, if we want to make them the same, we want to translate the f, which is basically this, to the 1 unit to the right. So if I do that, so basically this is your f of x here, and this is your f dash of x. So if I translate it 1 unit to the right, we're basically doing f of x minus 1. So if I sub that in there, damn, actually, no, this is a, ooh. That's why, this is hard because if you have to sub it into this x. So it will become like negative x minus 1, x minus 1 minus 1, which is negative 2. So look, this was this is what I wanted, but then I also would get this. But no, but this is actually a constant. So if you actually think about it, what if I expand this out? So what did we do first? This is basically what we've done is basically 1 unit to the right. 1 unit right. I'm just going to write these down here just to check them. And so basically if I expand that out, x times e, which is 1 to the power 1, because expand that out, so that times, so that's x minus 2. Okay, we're getting there. Now, the next thing that I want to get rid of is, you know, basically this over here. That e to the power 1. How do we get rid of it? Well, we'll multiply both. We have to multiply this whole function by 1 over e, which is basically a dilation by a factor of 1 over e parallel to the y-axis. So, multiply, so parallel, I'm going to write parallel quickly here. Y-axis. I'm just going to write them here. So I'll write them down nicely, but I just want to get them done. So it will become like f of, so basically it will be 1 over e in front of it, of f of x. So it will become, that 1 over e gets rid of it. So it will look like this. Now look at this. We're getting closer. Now the difference is this negative. That's basically a reflection along the, so if that's a reflection, no. It's not a reflection in the y-axis. So in the, yeah, y-axis, because that, what will happen is this will change, and that we don't want that to change. So, no. Actually, it's just a factor. So I can take this here. I can put a negative here. Sorry, I can put in like a negative here, and this here would become 2 minus x, which is basically negative x plus 2. So yeah, actually, all we have to get rid of that negative, we just have to reflect it along the x-axis. And they will get rid of this, because negative f of x will get rid of that. And yes, this here looks the same as that. So the next one is a reflection along the x-axis. Now these are I think there's probably many solutions to this, but yeah, 1 unit to the right looks good. Then, you know, 1 over e basically parallel to the y-axis and reflection along the x-axis. So let's write these transformations down. So the first one is, okay, so it's going to be a translation of 1 unit to the right. You can say, you know, to the positive x-axis direction and stuff, but yeah, so all the same, to the right. Next one we said was, you know, parallel to the y. So basically dilation by a factor of 1 over e parallel to the y-axis. Or you basically can say dilation by a factor of 1 over e from the x-axis. Basically the same. Beautiful. Next one we said was reflect along the x-axis. So reflection along the x-axis. Beautiful. And yeah, these are the 3 transformations that basically got me that to that. A little bit of, wait, that is actually a hard question. I'm not gonna lie. Like when I first tried it, I looked simple, but then I remembered that this here also gets transformed, which does a little bit change the function. So that's why you need to be careful. Yeah, but I think these are correct. Beautiful. They made that change. Yeah. Beautiful. Let's move on to the next one. All right. Let's use this color. Show that ddx, so the derivative of this is that. Easy. Again, product rule. How many product rules are we doing? So u is equal to this one here, negative x. And let v equal negative x, e to the negative. So u dash is what? Negative 1. V dash is negative e negative x. So remember the product rule? Multiply these two together. So basically it'll become x e negative x plus multiply these two together. So which basically becomes negative e negative x. Beautiful. And we see a common factor of e to the negative x, which is x minus 1. Beautiful. Does that look like f of x? What was f of x? Oh, not that one. F of x is, yep, e to the negative x, x minus 1. Yep, same thing, but just do this. Do that, put that there, right there. There it is. So, yeah. So here. So, yep. Beautiful. Which is equal to your f of x. Beautiful. Nice. Yep, so 1 mark. That looks good. D, I think D is the last part. Yes, it is. So D is the last part. Let g of x be the tangent to the graph of f at the point 3 to 3. Okay. Using the derivative that negative x e negative x is f of x, or otherwise determine the area of the region bounded by the lines x equals 1, g of x, and the graph of f of x. So basically the one that's shaded here. All right, let's have a look at it. We want this area basically. Okay, so is it hard? No, it's quite simple. So, yeah, it's actually quite simple. So x equals 1 here, line, and so only going from x equals 1 to 3, the top function is your g of x, which is that tangent to 3, the x equals 3, which we can easily find for calculus. And so that g of x minus the bottom function, which is f of x, and that will give us this area. This is actually, wow, very nice. Is that the last question? 4 marks. Probably because of the algebra. There's going to be a lot of algebra. But yeah, so wait. So let's write the integral. So to get the area, it's going to be basically 1 to 3. G of x minus f of x dx. Beautiful. So this is what we basically need to simplify. Now, let's find g of x, which is our tangent. Easy. Now, remember how to find the equation of a tangent? We need to get a point on it and a gradient. Now, we already know a point on it, luckily. So, which is 3 and f of 3. Now, f of 3, let's find it. Let's go back to f of x because I don't remember what f of x is. So if I sub in 3 here, so 3 minus 1 is 2e negative 3. So 2e negative 3. So 2e negative 3. This is a point. So this is that point. And we also need to get the gradient. So the gradient's quite easy because we did get the gradient. We just sub in 3. We did calculate the gradient, which was here. Yep, this one over here. So the gradient, if I sub in 3, it'll be e negative 3. Wait, I'm just mixing them up. So 3, we're subbing 3, yep. So e negative 3 plus 2. So basically 2 minus 3, which is negative 1. It's negative. So negative e negative 3. Negative e negative 3, yep. Negative e negative 3, which makes sense. It is a negative gradient. You can see it's going down, and yeah, this looks great. So g of x, to find g of x, is basically, so using your equation of a tangent formula, so y minus your y value, so 2e negative 3, equals your gradient, which is negative e negative 3, times your x minus 3, the x value. So simplifying this, we get the equation. So y equals negative e negative 3x plus 3e to negative 3 plus 2e negative 3. Y is just basically g of x, sorry. Just write g of x. It's negative e negative 3x, which is plus 5e negative 3. Done. So we got our actual g of x. So now, of course, f of x, f of x, you can't integrate that. Yeah. We have to, yeah, hell no, we can't integrate that. So yeah, that's why they've given us this over here. So actually split this up. Let's split this up. So 1 to 3 g of x. So g of x is what? Negative e 3x plus 5e negative 3 dx minus the integral from, again, 1 to 3 f of x. Now, I'm not going to write f of x because we can't integrate it, but luckily we have this here. Because we know the integral, if we integrate both sides here, it's the same as this, and these will cancel out. So basically the integral of f of x is this over here. So this is great. So I'm now going to integrate this first, which is basically negative e negative 3. Remember, this is a constant. We have x here, so it'll be x squared divided by 2. Plus, this is a constant, so it'll be 5e negative 3x from 1 to 3 minus square brackets. So now we know the integral of f of x is this here. So that negative x e negative x from 1 to 3. And this is our goal. Now we just basically simplify this. So let's sub in 3 as for the other one. Yeah, so if I sub in 3, it'll be squared. So it'll be negative 9 e negative 3 on 2. Yep, so 3 squared is 9. Yep. That looks good. I just don't... Yep, so plus 15 e negative 3 minus... Now we sub in 1. So negative e negative 3 divided by 2 plus 5e negative 3. Close the bracket there. Minus, now we do sub in 3 to the other one, so basically like negative 3e negative 3. Yep, that works. Yep, minus, just be careful, there's a lot of algebra here, so you don't want to make mistakes. Negative e negative 1. There it is. Okay, made some progress. Now we just need to simplify this. Let's just expand everything. That's that. Plus 15 e negative 3 plus e negative 3 on 2 minus 5e negative 3. This just becomes plus here. So it becomes plus 3e negative 3 minus e negative 1. Beautiful. So 15e negative 3 minus that is basically 10. So we can get rid of this here. Be a 10 here. Also, 10e negative 3 plus this is actually 13, so we can get rid of this. This one over here, because of the fractions, basically it's like negative 9 on 2 plus half. So negative 8 on 2, which is negative 4. So this here is negative 4. So basically this simplifies to negative 4. And so negative 4e negative 3 plus 13, that's going to give me 9e to the negative 3, so 9. Just put 9 there. Minus e to the negative 1, which is here. And so that's simplified. That's your actual, yeah. So that is equal to 9 over e3 minus 1 over e. That is your area. Unit squared. There it is. Perfect. Yes, we are, we have completed this paper. I hope you guys enjoyed this video. Please make sure to like and subscribe for more future videos like this. I hope this video really advances your method skills. I try to go in very deep detail of every question. Good luck to all students this year. I hope you guys do the best. Please get rest. Try your best. It's not the end of the world if you don't do well, but just try your best. It's all worth it. Believe me.